So in that context, it's a pleasure to be able to introduce Peter Smith today, who is PI of the Phoenix mission. I stumbled over is versus was, but I presume PI-ship lasts forever. In that context, Peter has made the mission happen and enabled the science, and he'll be reporting to us about it. Before I let Peter speak, Peter, if you could come on up here, I have a presentation. The AGU provides this nice certificate to Shoemaker lecturers, to the named lecturers, and this one says the Planetary Sciences section recognizes Peter H. Smith, the 2008 Shoemaker lecturer for the Phoenix mission explores the Martian Arctic. So Peter, thank you and congratulations. And now Peter Smith.
Thank you, Bruce. Now don't start using that was before I'm done here. He's anxious to get started with his scout mission, and it's a little bit like passing the mantle here, so it's kind of an exciting time. I wanted to show a picture of Gene Levy, who, to tell you the truth, I missed Gene Levy being at this meeting. He was...
Gene Shoemaker. You misspoke.
Oops. Can I start over? I knew I was going to do that. Gene Shoemaker. I miss Gene Shoemaker at these meetings because he was such fun, and this is a great picture of him, that wonderful smile. He'd be around the posters, and he would be always such a joy to talk to because he was so excited about the science you were doing. And I think he'd be particularly enthusiastic about the science that Phoenix is doing because we landed on the ejecta of an impact crater on Mars. And that would have been the type of terrain that he would have loved to look at and theorize about. Now, the other thing on this picture is our logo, which is, of course, Mars with a big water droplet and a fiery phoenix bird. And that has some symbolism for us. The phoenix bird being the symbol of rebirth. It is reborn from the ashes of the previous bird that lived for 500 years in mythology. And because of that, it's very much like our mission. Our mission was the rebirth of the 2001 Surveyor lander that was canceled after the loss of Polar Lander. And so we were able to bring that mission back into a vehicle that could really do the job that we wanted to do in the polar region on Mars, and therefore the phoenix bird became our symbol. But also the symbols of fire and water, as you'll see as I go through my talk, are very important for the kind of science we're doing in this mission. But of course this isn't done by one person. We have a very large team, and this is our operations team in front of our operations building at the University of Arizona in Tucson. And behind us is a mural done by the University of Arizona Art Department. They had a class on mural painting, and we gave them a section of our wall to do a mural about Mars. And really it shows the transition through time and space from mythology to engineering to Mars. And really this talk is only doable because of the work of this huge team, and we kind of appreciate working across the campus with the art departments, and even the dance department did a Mars theme one time. So we've tried to use this mission to reach across from science to art. Now, we launched in August 4th, 2007, and this is from Cape Canaveral, and you can see our logo on the rocket, so you know that I'm not making this up. And it's 130 feet high, 9 solid rockets. It's really quite a wondrous event to watch a launch of this type. But this one's particularly wondrous because it was at 5:26 a.m. and dark. You could see the stars, and when it was ignited, it lit up the entire sky, and you could watch it move all the way across through Orion's belt over the horizon and around the planet. Well, you couldn't see that, but it went over the horizon anyway, and it left an incredible vapor trail behind it. And because the sun was just coming up shortly afterwards, it lit up this vapor trail. And to me, one of the most astounding things I have ever seen is the shape that this vapor trail took after the sun lit it up and the sky was still dark. And that's in this picture. And I've drawn a little outline around it for those of you who are skeptical. You can see it's a phoenix bird, and just made the most incredible impression on all of us who are watching the launch. So where are we going? We're going to the northern plains of Mars, which is usually colored blue and kind of hopes that this was an ancient ocean. Many of us would love for our neighboring planet to have been the kind of Earth-like environment that we enjoy here, and perhaps even a place where life could exist. And so that kind of motivates, I think, many people in enjoying the different Mars missions. So there we are, way up in the northern plains and down at an altitude of -4 kilometers, 4.1, and really quite a different environment than the other landers, particularly Spirit and Opportunity, which are looking at very ancient environments. We are looking at a modern environment. But even though the phoenix bird in the sky gave me a lot of optimism and hope, not everybody was enthusiastic about our landing, and there was a lot of worry and concern, and particularly some of the upper administrators really weren't. They hadn't seen the phoenix bird, I think, in the sky, and they thought maybe things could go wrong. And indeed, there are a lot of ways in which things can go wrong as you land on Mars. It's a very complex endeavor, and it's only through the skill of our combined team at JPL and at Lockheed Martin that we really reduced risk on this adventure. But of course, Mike Griffin and Ed Weiler were really worried that if it didn't go well, there would be a lot of consequences, and they had their fingers crossed for sure. I wasn't quite so concerned over here. I was eating peanuts, which are, of course, a good luck. And anyway, we managed to land safely on May 25th using the old-fashioned method of thrusters, and I think this is perhaps the way of the future. I think Mars Science Laboratory, of course, is going to use thrusters. They have some sort of, what do they call it, sky crane, yes, and so it's even more ambitious than this. But it worked beautifully. It was absolutely flawless and a thrilling landing. So as we came down, we landed in a little valley at 68 degrees north, and here we are on this is the Heimdall crater, and the ejecta blanket actually covers a lot of this valley. So we are right on some of the output from this crater. And as we were going down, we were getting communications through the Mars Reconnaissance Orbiter, which wasn't quite in this line, but probably over here somewhere. But it was tracking us down with their radio antenna. And since the radio antenna was tracking us, that meant the camera was pointed in our way. And Alfred McEwen was able to snap off a picture and notice the crater in the background. And I think many of you have probably seen this, but it's absolutely astounding picture of there's our parachute, and here it is blown up. You can actually see the wires holding the parachute to the back shell, and incredible tour de force for one spacecraft to take a picture at another during that time of parachuting through an atmosphere. Really an incredible picture. I think this has to be one of the top 10 for the decade, in my opinion. Well, this is a little dark, but also the HiRISE telescope was able to take a picture of our lander, and here it is exploded a little bit so you could see it. You can actually see the solar panels and the lander deck. And you can see the terrain around it is kind of bumpy and lumpy, and this is a real polar terrain, which is indicative of the ice underneath that expands and contracts, and when it contracts, it can form cracks in which soil and dirt and sand can get into the cracks and make it very difficult for the ice to expand back where it was. It's going to have to form some bumps instead. And so over the years of expanding and contracting, it's formed a rather chaotic surface, kind of a pattern ground it's called. We can also see the back shell with its parachute and the heat shield where it hit the ground. And notice also that when things hit the surface, there's kind of a dark area formed, and so it kind of indicates there's a little bit of brighter dust right on the very surface of the Martian soil there. And this is our spacecraft with the instruments labeled, and they come in three groups: weather and climate. Really, we've enjoyed partnership with the Canadian Science Agency and York University and MDA, and they built a LiDAR and temperature sensors and pressure sensors and a wind telltale that blows in the breeze, and we can take a picture with our camera. That actually worked remarkably well throughout the mission. Pretty much a zero-cost experiment for us, and no data rate at all. We just take pictures of it. And then we have physical geology, which is, of course, the combination of cameras, and this is a panoramic camera, a robotic arm which can dig into the soil, and it's a bit like a backhoe. It can only dig straight back towards its elbow joint, and it has a camera on it, and it has a thermal electrical conductivity probe we can put in the ground, and I'll have more to say about that. And then we do mineralogy and chemistry with two instruments. A TIGA instrument, which has 8 ovens, only one-time use each, so we have to be careful about using these ovens, and also connected by some plumbing to the ovens or some a mass spectrometer that will tell you the type of gases that come off, so you know the temperature at which gas comes off, you know the depth in the soil at which you got the sample, you know if there's a calorimeter inside of these ovens too, so you can actually tell if it goes through a phase transition, and you can tell the isotopic ratios of some of the gases that come off. So there's a lot of information in this instrument, and for that reason, it's not a quick analysis once you get the data set. It really is quite complex to deconvolve all these different things that are going on. And then we have our Mecha instrument, which is both a microscope and you might even call it a submicroscope, because there's an atomic force microscope that can see down to, I think its entire field is 16 microns, so the resolution is down near a micron or less. And so that's in this box back here, and we also have 4 wet chemistry cells. And so this is the fire and water I was talking about as our themes. We add water to the soil, and we kind of simulate a time when the soil might have been wet, either in the past or the future, and we look at the chemistry that's happening in solution. And then we can also heat the soil and look at the minerals, and particularly we're looking for aqueous minerals, those that form through the action of water. And okay, so the first thing we did after landing and taking a look around was to take this arm and point it back under the spacecraft. We had the task of making sure that each one of our lander foot pads was securely on the surface and not tilted on a rock. So when we did that and looked straight back under the surface, we were absolutely amazed to see that the thrusters had blown the soil away from an ice layer. Well, many of us thought it was an ice layer, but of course there was no proof it was ice just looking at this. It could have been rock or salt. But right away, this is exactly what we're looking for, and you can see by the curvature of a shadow of a straight strut that this is at some depth here, and the depth turned out to be about 5 centimeters. So a very flat table of hard material, which we now think is ice, and blown away by the thrusters. Also, we took panorama with the camera, and we see a very flat surface. We see this patterned ground. It's not as polygonal as you might think it should be when it's called polygonal ground. It's really kind of more of a chaotic lumpiness, and we could actually trace all these things. And some of these little fractures look very, very recent. So we think this is still an actively forming surface here. It's not something that happened many millions of years ago. It's probably fairly recent in its formation. Some very recent cracking and some other examples of that which I won't show. But and then we dug trenches around in this digging area. We had about this big an area where we could use our arm, and we could dig trenches and look in, and of course the first thing we find is there's bright material, looks just like ice, but it doesn't, in this case, look like it's mixed with much soil. It's just pure ice, or very little soil component. Notice this rock with a tail behind it. It was actually moved by the thrusters. So when you're on an ice table, things move fairly easily, and that rock slid along and made a little trail behind it. And in our digging area, we've mapped it and given a little topographical map here. We see, and this is what we're hoping to find, is that we find the high areas of the polygons and the low areas in between, both within reach of our robotic arm, so that we can dig on the top of a polygon and in a trough. And this is important because on the Earth, when you study polar regions, there can be real differences between those two parts of the polygonal ground. So we were very happy to see that we had the opportunity to do that. And there's a whole series of trenches here. I think we dug between 12 and 14 trenches, depending on how you want to count them. And the greatest depth we were able to get in the trough was about 16 centimeters, and on the top of the polygon it was more like 5. So there really is a difference between these two types. And while it's a little difficult to see, on the left there's some little flakes that were scraped off of this white layer here that immediately clued us into it being ice. And so on Sol 20 we found 3 scrapings off of this ice, and Sol 24 they had disappeared. So it's maybe a little tough to see this, but there's 3 right there, and here they're invisible. We can stretch these pictures and see for sure, but that right away told us they were ice. But that wasn't enough. We had to get a sample of it and put it into our TIGA instrument and actually measure it being ice. And it took us 3 weeks to do that, but we were successful, and by gosh, that is ice. H2O, water ice. Melts at 0 degrees. And then we could move some rocks around too. And so here's a rock that we dragged across the surface, and the idea being to try and get a sense of the topography of the ice table underneath the soil. And we have been successful in finding out that the soil under the rocks is actually, the ice under the rocks is a deeper depth than next to the rock, and that the rock acts as a heat source and can actually lower the ice table as predicted, but the amount of lowering is what's important. So because of all these examinations of the ice and the soil and the placement, we're able to validate models that were made from Odyssey that were showing that the ice would be a certain number of centimeters under the surface. But there were a lot of assumptions that had to be made about the properties of the ice, the properties of the soil, its the ability of how much water would be in the upper soil, how well packed it was, the pore spaces, and that sort of thing. And so now we can constrain those models, now that we have a really good sense of the actual depth and the properties of the soil above it. And I think by constraining the models using this as a tie point, we can make a better map of the ice under the surface in the entire polar region, and I'm expecting that to happen over the next year. So the ice properties are, and here's one of our trenches, and these little cuts into the surface are caused by a rasp we have at the end of the arm. And this is important because when you're trying to get a sample of ice, it's very hard to scrape it up. This ice is at minus 90 centigrade, and when you scrape on it, it's extremely hard, and even with our hardest scraper made of tungsten carbide, it's very hard to get a sample of. So we brought a little rasp with us, and that rasp, we could spin chips of ice into the back of our scoop and therefore deliver pretty much pure ice, or pure ice soil mixture. And so that's the array that we would make 4 by 4 using those little rasp diggings. It didn't take much to fill the scoop, so a little patch like that, and we had a good scoop full. But unfortunately, when we tried to deliver that scoop full of ice, it stuck inside of the scoop. Darn the luck. So we had kind of a real difficulty in knowing what to do about this, and we found out that if we put it into the sunlight, it came out easier. So, or was it the shadow? I think it was the shadow, excuse me. So if you had it in the shadow, it came out easier, and so we had to develop a whole method of bringing the arm up, keeping it in shadow, and then dumping the material out. But even then, it was very hard to get into our instrument. So the polygons are 2 to 3 meters in size, implying a soil-ice mixture based on some models by Mike Mellon. And it's formed by, we think, thermal contraction, and is a currently active process because we see some very fresh-looking cracks between the polygons. The hard ice layer is between 5 and 15 centimeters beneath the surface. It's deeper in the troughs, and this validates, as I said, the orbital measurements and the interpretation of those gamma ray measurements that could sense the ice in the first place. And I think we'll be able to improve those models. And it also helps us understand the vapor diffusion models that also predict a depth to ice. And so by improving these models and interpreting the observations according to this calibration point, I think we're going to be able to do very well. And again, the rocks depress the ice table. So now here we are delivering samples. There's a sample in the scoop, and you can see the solar array in the background. It's still pretty clean. This was early in the mission. And there's some soil in the scoop. And the robotic arm camera right here can actually take pictures in the scoop so we can document just what materials we've collected. And here's a picture in the scoop, and this one shows some icy material on one of the clods. But notice also that this soil is all of a cloddy nature. It's all lumpy, and these clods have caused us all kinds of trouble because we have a screen with 1 millimeter holes. And while if you were to take this material and squeeze it between your finger, it just goes to dust, or powder if you like. But when it forms clods, it's bigger than the mesh size. So how do you get it through the screen when it's going to do something like this? And that's been one of the real difficulties of our mission. So here's the material dumped on a screen. Here's a screen that before any material is dumped, so you can see it's got a lot of holes in it, but it's also tiny holes compared to these big clods that are falling on it. So we have the ability to shake, but when we got there, we found that shaking up and down wasn't the right way to do it. Probably left and right would have been better. It's more like sifting flour, so you have to kind of push it through the screen. And I think that's a lesson learned, but unfortunately it's not going to help us any. But the other thing we had trouble with is the doors wouldn't open all the way, and so here they are, unfortunately not opening. We had to learn how to pour material through this little triangular opening at the upper end. This is on a 45-degree slope, I should point out, and these doors are maybe 3 inches wide. But you had to pour the material through the end of those doors, and so this was a real challenge, and it took us a lot of time to try and get material in the ovens. But we were successful in getting 5 ovens filled with real Martian soil, and that, I think, was quite an accomplishment considering our difficulties. And what we're able to identify from the TIGA instrument is the ice at the bottom of one of our trenches called Snow White. We found that 5% of the soil material is calcium carbonate because of a high temperature release of CO2 and a reaction inside of the calorimeter. And we saw other aqueous minerals, but we have several candidates for these, so it's hard to know exactly which aqueous mineral this might be, but definitely it released water. So we think it could be a phyllosilicate, and there's really many other types of minerals it could be. But the one thing we didn't see was sulfates, and this was a big surprise. We came to this landing site filled with ideas from the MER mission that this might be an acidic environment with lots of sulfates, and we're really pleased to be able to identify just which sulfate it was, which would help us in our interpretation of, at least some of the scientists on our team, with the interpretation of the MER data sets. But frankly, we weren't able to measure any sulfates at all with either instrument, and now we're still struggling to see maybe sulfur could be there in some other form. We're going to have to go to the laboratory to try and see if there are types of sulfur compounds that we wouldn't see in these in either the wet chemistry or the TIGA instrument. But somewhat of a mystery why there aren't any sulfates, and yet the soil seems to be a loose soil that could have been blown in. So here's the scoop delivering to the wet chemistry cell, and this is the little opening here. It has a screen over it, and you can see we've been putting material into the microscope thing, which is just off the entry port, which is right here, and some of that spilled over. I should point out in the background there's a little DVD there, and if any of you are ever in the northern plains of Mars, this is a free lending library. So it's got all the Martian books that I loved as a child, and the Planetary Society put together a group of books by Heinlein and Bradbury and Clark and all the great science fiction writers who wrote about Mars, as well as some essays about Mars. So it's right there. It says, astronaut, take this with you. And it may outlive human civilization for all I know, but it'll be there a long time, and it's kind of a unique time capsule in a way. Okay, so what did we learn in the wet chemistry? Well, the pH is about 8.2, plus or minus a half, and it's an alkaline soil and controlled by calcium carbonate. When we added an acid tablet, the calcium carbonate buffered the solution and the pH did not change markedly. So we're very sure that calcium carbonate is controlling the pH of this solution. A pH of 8.2 is kind of interesting because I'm sure many of you know this, but that's about the pH of ocean water. And many soils on Earth have this sort of composition with a pH of about 8.2 and calcium carbonate. So that's not unusual on Earth, especially in dry environments. We also saw, which was a huge surprise to us, 1% perchlorate ion in the solution, and it's probably magnesium because there's a lot of magnesium in there too, but of course you only see the ions, so how they fit together isn't 100% certain. And the magnesium perchlorate, there could be other types of perchlorate in the solution too. So perchlorate, for those of you that aren't familiar with it, is the oxidizer in the rocket fuel that we used on our solid rockets. That's ammonium perchlorate, but it's a chlorine with 4 oxygens, and of course as a rocket is going up through the atmosphere, you quickly run out of oxygen to burn your fuel, and so you got to bring some with you, and they use perchlorate as the oxidant in the fuel. And so it's become a contaminant in groundwater, because where they make the rocket fuel, sometimes it spills out onto the ground or gets into the environment. It's extremely soluble in water, and it can percolate down through the ground into the groundwater and become a contaminant for drinking water. And the way that people reduce the perchlorate in their drinking water is with bioremediation. There's lots of microbes that can live off the energy of the perchlorate. Usually they're redox couples, and they're using the energy exchange as perchlorate accepts electrons. And so we have a material that on the Earth would be an energy source for microbes. Now on Mars it may not be, but on the Earth it could be. So very interesting material. The other interesting property about perchlorate is that it's somewhat toxic, and that's why they try and get it out of the drinking water. And you have to be careful, I think, as an astronaut. At least you want to know that perchlorate is there. It's not terribly toxic, but you want to protect yourself in some way, I would think. You wouldn't want to be breathing that for a year, so especially at these levels. And there are tiny amounts of salts, potassium, chlorine, and sodium. So that's kind of where we are. I think there's more to be learned from the wet chemistry, but it's not going to be certain what we know until we actually go to the laboratory and spend some months trying out mixtures of these types of materials and looking at the signatures. Okay, the microscope was really fascinating. We were able to see 2 clearly identifiable size distributions. There's a very fine clay or silt-sized component. And then, since this is a magnet, all clustered at the strongest part of the magnet are a bunch of brown particles. Here's another example. Lots of different colors, but clearly rounded, almost football-shaped, which kind of makes you think that they're saltated along the ground, and that's how they get weathered. Saltating, these are 100 to 200 micron particles, just about the right size for saltation, which means that you flip one particle up and it bounces up another one, and it goes across with the winds very low to the ground. And the very fine material, of course, which is orange color, which I think is really the Mars color, and we've put these colors on top of our images from the panorama, and we can see they're the same color. This is the material that I think is globally distributed on Mars. So it's quite a question. If this is globally distributed and you see lots of sulfates at the MERS sites, why aren't we seeing sulfates with this material? So not sure how to answer that question, but that's a very fine material there, and then 100 to 2 micron grains that are probably saltated, and of course we see larger rocks and other things that have been here for a very long time. But I'll tell you, we spent 150 days putting samples onto the spacecraft and into the different instruments, and after a while the spacecraft got to be a little messy, so I have a picture that kind of shows just how bad things can get after 150 days of dumping soil on a spacecraft. So it's really got to be a mess. And of course, the Opportunity rover came up to see what was happening, and they call for help here. Now, we also studied the weather in this mission, and this was, I think, really an opportunity for us to make a big contribution, because polar weather, of course, it's been studied quite a bit from orbits, but you build up a lot of clouds in the polar region and you can't see very deeply in the atmosphere, so you're not sure what's happening in the lower scale height, and that's, I think, where all the action is. So polar weather is really an opportunity for the Phoenix mission to make a large contribution. And what we saw after landing, this is our latitude, and this is the water vapor in precipitable microns as measured by TESS and published by Mike Smith. And these are the different seasons. So we landed at 68 degrees just at the end of spring and lasted through 3/4 of the way through the summer season. But for the first part of the mission, about the first half, and I think actually the first 90 sols of the mission, we were measuring dust clouds, dust blowing by at a scale height of 4 or 5 kilometers, or a boundary layer of 4 or 5 kilometers. Only dust. Didn't see water clouds of any sort. But starting very abruptly at this date, now we're seeing clouds and even ice precipitation. So a very abrupt change, maybe not quite where you'd expect it at the highest humidity values as measured from TESS. So a bit perplexing there as to why this region isn't over here. And I think our team is coming up with some answers to that. They haven't fully developed them yet, but I think it's going to have a lot to do with the local forcing of the atmosphere rather than forcing from the polar cap, which of course is a tremendous source of water in the summer and probably responsible for most of this. Of course, it's getting late in the year about this time. The sun is going down, so we had finally dark nights, and we're seeing some frost on the ground. This is an example with the LiDAR, and let me explain this plot. This is altitude on the left and time. And so the LiDAR looks straight up, just like I could point this laser straight up, and then the cloud blows by and the local winds. And so you're getting almost a cross-section through a cloud. It's like cutting a section through a cloud, except it's both in space and time. So the cloud's blowing by, but time is also changing. So the cloud can go through morphological changes. There could be gaps in clouds. So it's a little bit of a strange picture. It's not taken all at once. So you have to understand that. And what we see is a very high population of water ice crystals between 3.5 and 4 kilometers at about 4:30 local time. And then after about 5 o'clock, we see these fall streaks. Now, fall streaks have been very well studied on the Earth with LIDARs, and these are, for those people that use LIDAR, this is a very strong indication that ice particles are leaving the bottom of the cloud. We think the particles can be as large as 20 microns, and they fall down, I guess they form up here, and then they grow, and then they start to shrink again. So they go through kind of an evolution from the top of the cloud to the bottom. And this is probably enough snow that if it all fell on the ground, it'd be a few microns deep. So it's not a big snowstorm. It's not like on the Earth, but still, if you were on the Earth, you could see fall streaks under clouds too. And here's an example.
What's the wavelength?
The wavelength is 1 micron, 1.06, I think. Another way of studying Mars is to use our thermal and conductivity probe, and that's at the end of the arm. And here it is stuck into the ground, and since, of course, you can't see the end of it, here's what that probe looks like on the left. It has 4 tines on it, and by heating one and sensing temperature on the next, you can measure the thermal conductivity, and you can also measure electrical properties in the soil, as well as the humidity. There's a humidity sensor on the side. The humidity isn't in the ground. It's several centimeters above the ground. But you can measure humidity, and you can also watch what you're doing with the robotic arm camera, which can see exactly where it's placed in the soil. And so we used the humidity sensor quite a lot, and we took a few measurements in the soil too, but not as many as we would like. And if we look at some of the humidity measurements, let's see, this is time here. This is partial pressure of water from 0 to 3. And from midnight to the morning, well, let me look at the midday. Midday, we're at an average of about 1.8 pascals of humidity just above the soil. But clearly, as the sun gets low in the sky, it drops very rapidly down to very close to 0. So the water vapor in the air is dropping down to the ground. Humidity goes very low. So, and then in the morning, it comes back out of the ground up into the sky. A bit of a surprise. And the actual relative humidity, because of course temperatures are changing across here, at night it's essentially 100% humidity. That's why it can saturate the atmosphere and come out. And then in the daytime it can be, depending on which part of the mission, between say 5 and 15% relative humidity. So these are really nice measurements, and I think we're going to learn a lot by studying these in relationship to the clouds and the temperatures and the pressures. One of the hopeful ideals of this mission was to say something about habitability. Now, we all knew that at this epoch of Martian climate that it's really cold and dry. But we understand that as you go back in time, it can get warmer because of the orbital dynamics and the obliquity changes. Mars doesn't have a large moon, and it's closer to Jupiter, and both of those things affect the spin axis tilt. So really, we wanted to know if in earlier times we could see any evidence that this was a wetter soil, and were there nutrients and energy sources that would make you think that if you had microbes living here, at least at the wetter times, they could survive, and if they were smart enough to go dormant for the very long times in between, you know, you might have some kind of biology. So that was a hope, but you know, you got to have a dream after all, and that was our dream. And so we know we're going to find liquid water right now, as this area's been studied, and it's very unlikely. But could they have been wetter? We do have that energy source that on the Earth is used for powering or giving energy to microbes. We have nutrients, and we also had taken a trip last year to Antarctica with the idea of doing the same experiment in Antarctica that we were doing on Mars, digging a trench, looking at that ice-soil boundary, and trying to understand if this is a habitable zone for microbes in the very driest, most Mars-like conditions on Earth. And We went to very low valleys, which are near the ocean at 100 meters altitude, and dug trenches and looked at the material and did biological analysis and mineral analysis, but that's not complete. And then we also went up to high altitude, 1,700 meters, where essentially you're out of the rain zone. There's no liquid water for at least a very long time in the past. And while you do get little patches of snow, it tends to sublimate away and not go through a melt phase. And what we found was the ice table in this high valley, University Valley, which is near Beacon Valley, for those of you who have been in the dry valleys of Antarctica, is with a 30 to 35 centimeter trench. We could take a chunk of the icy soil, bring it back in pristine conditions to our laboratory, and find just as many microbe counts in the high valley as in the low valley, where there's lots of liquid water and you would expect communities. But what the difference was is there was less diversity. There was just one or two types of microbes that could survive up here, whereas there's a much bigger community down there. And so we're getting to the point where we're trying to publish some of this data about very cold conditions on the Earth with ice soil and microbes living in that soil. And basically the biologist on our team says microbes are really smart about finding a way to live. Even in places where there's not liquid water, they can find ways to attach, mist or absorbed water to themselves and try and use it. So we have a lot to learn about even life on the Earth, much less Mars, which of course is another step beyond in dryness and coldness. And here's a chart from a paper by Levrar from 2007 comparing the oscillations of the obliquity and the changes in insolation in the polar region to going back in time. And this is 10 million years back in time, and at the present we're at an insolation watts per square meter. Now this is an average over a diurnal average, and also taking into account the length of the summer season. So it takes both into account. It's an average illumination, not one you'd see on any particular day or hour, but watts per square meter, and we're at about 250. And what they found was at anything under 300, basically it was bringing water from the equator towards the pole. The pole was a collector of water vapor and was growing. But if you got above 300, then the situation reversed very rapidly. The pole became unstable, and water was being dumped as fast as possible, depending on how far above this line you are, being dumped into the atmosphere and transported towards the equator. So if you can just get back even 500,000 years to get these little spikes above the line of 300, you have an unstable polar cap, and unlike today, now you have a tremendous source of water vapor into the atmosphere and chances for much higher humidity. And from what we're seeing now with how important humidity is to controlling snowfall and local processes, I think these are the kind of things that aren't in the current models, and these models will have to be modified to take into account what actually happens at our landing site. So, the conclusions, the Odyssey ice cover and discovery were validated by Phoenix. They pretty much found it right where they said it'd be. This is William Boynton and his team at the University of Arizona. And the shallow placement of the ice agrees with vapor diffusion models, and certainly some of the ice-soil mixtures are very high in soil and therefore could easily have been formed by diffusion into pore spaces. However, we also saw ice that was very pure, and makes you wonder, why isn't all the ice the same, and why is some ice different? It seems to be out of balance with the rest. So we don't have an answer for that, but that's certainly one of the mysteries we're trying to unravel. We had unexpectedly an alkaline soil, the pH controlled by calcium carbonate. And it's very much unlike the acidic sulfate-rich soils seen by the MER rovers, and this was very much a surprise to us, and our instruments weren't really, peaked for or tweaked for that sort of environment, but we could still handle it. not likely a habitable zone today. There's really no liquid water in the soil at all, and maybe a little bit of absorbed water at night when the water drops out of the sky, but not much. And other requirements for life are, at least if this were the Earth, they would be energy sources and nutrients. Who knows what Mars microbes live on, but they are potential energy sources and nutrients. Our 150 sol weather record through late spring, summer, and summer brings a lot of surprises. Ice precipitation, ground fog, local forcing of climate. The GCMs really are going to have to take this into account, and I think this may be one of the big contributions that Phoenix makes to the Mars community, is giving another tie point for these climate models, and I think they're going to have to be tweaked, and as they are now, they wouldn't predict the kind of environment or the kind of weather that we see. We also see a cloddy soil, calcium carbonate rich, and, well, 5%, and aqueous minerals. Water was important in creating this soil, and could have been through these obliquity cycles that I just talked about. Another possibility, it was this impact, and certainly we're on the ejective blanket from that impact. Could that have had a big role in putting the water into these soils? Well, that's certainly a possibility. And that impact we estimate is about 500 million years ago, 500 million years ago, based on crater counts. So other possibilities are, the impact, or maybe the soil came in from another region, who knows where, and that was a water-rich region. It could have been an ancient soil that, goes all the way back to 3 or 4 billion years ago, when we know Mars was a much wetter place, and maybe it was formed at that time. So there's no label on the soil. You have to make these determinations yourself. So we're going to have to argue, build a case for one way or the other. But the cloudiness means that, and the lack of dune features, and the rocks aren't modified by the wind. It's certainly not a very aeolian-rich place today. So who knows in the past. Anyway, these are the models from Odyssey. We landed in this spot. This is summer and winter. The blue represents a lot of ground ice in the upper meter of soil. And just by landing in this one spot, I'm hoping we can help understand this entire blue region over time. As we start to understand our site, maybe we'll understand the rest of the polar region better too. So the near future plans, laboratory testing. We've got so many different ways that we can see these signals that we have to just go into the laboratory and try and find out what works and what doesn't before we can say what is causing the low temperature releases in Tiga between 300 and 600, releasing both CO2 and water. There's just a long list of possibilities here, and you've got perchlorate in the soil that's oxidizing it, and so there's a lot to be done in trying to understand these signals. There is the potential, of course, for other carbonates, aqueous minerals, but even oxidized organics that are oxidized to the point where they release CO2 but not organic material, because that's very likely to happen here. But we haven't done that in the lab, so we don't know. And the complex chemistry taking place in that beaker, it's a small beaker, but there's a lot going on inside of it, and you really have to try a lot of different mixtures before you can match the signatures that we see from the 25 sensors that are connected to that solution. So the models to explain the ice-atmosphere interactions are just being started, and I think we need to develop better global climate models in the sense that they fit all the available data today, but they won't fit the Phoenix data. We're pretty sure of that. So we're going to have to work with the people that make those models and tell them how to adjust them, or at least they'll tell us how to adjust them, and we'll tell them what they need to match. So on November 2nd, Phoenix entered the Sleeping Beauty mode, and people are always asking me, what's going to happen in the spring when the sun comes back up again? And that's really a question of whether the prince will come. Thank you.
We have time for some questions, and I'm going to take the chair's prerogative and ask the first one. Peter, you talked about the using the Phoenix data as a validation of the vapor diffusion models, yet the diffusion models don't predict that you would have such a clean ice. They would suggest an ice dust or ice dirt mixture. Can you comment on that?
You're exactly right, and this has been pointed out more than once by our science team has various factions, and one of the factions is a believer that this, what seems like very pure ice, has come from a very different origin. It's certainly not vapor diffusion. And they suspect, and it's one of the somewhat tragedies of the mission, that we didn't actually get a piece of that into our instruments, but they suspect that there's some of the salt that we see involved. Because perchlorate is so soluble that if there was ever any tangible liquid water there, it would go into solution and it could pool, and that might form a more pure ice if it could, flow out of the ice-soil boundary and into a purer state. There's other ways to get pure ice too, which Mike Mellon would have to explain, but he doesn't seem too upset about it, and frankly, it's kind of a mystery to most of us. So I'm sorry, I don't have a good answer. Are there easier questions here?
Just go ahead and call on Peter.
Yes, sir.
Peter, what can you tell us about organics in the soil?
Be nice if they were there, Carl. Well, the problem is, if you had an organic-rich soil and you mixed in perchlorate and stuck it into Tiga, you'd see CO2, which is what we see. But does that prove there's organics? No, because if you mixed carbonates of iron and magnesium carbonates in the soil and put in a little perchlorate and put it in, you could see the same signature. So without going to the laboratory and actually putting these materials into our 4 remaining Tiga cells that are the exact same configuration as flight, we really aren't in a position to make a statement about this, except maybe. And that's not very satisfying. So you're just going to have to be a little patient on this one and wait for us to do the laboratory testing. And even then, this is not an easy question, and there's probably going to be some controversy. Yes? Yes, we've talked a lot about that. There's iron 2, and I think there's probably a number of materials of that sort. We're not sure about sulfides, but I think there probably are electron donors in the soil, but we haven't identified them specifically. And of course, when you say a habitable zone, that doesn't mean that there's actually things living in it now. If you brought in material that was living in it, maybe they'd bring the reducing agents with them, because organic material is also a reducing agent. Just a thought. In the back? Well, yes. I don't have the answer, but there's kind of a first look at that, but I'm sorry, I can't tell you. That we can measure the isotopic ratios both at the low temperature and the high temperature release, and both C1213 and oxygen 1618, I think they're both measurable, but whether our calibration is at the point where we'd want to release numbers, I think not. I don't know if Bill's in the room. He's the person to talk to. Bill, can you make a statement on that? But they're coming. Bill says yes. Over here.
Calcium carbonate, 5%, does that solve the missing carbon inventory problem?
Well, if we had an orbital mission and could measure it all over the planet, we could say something about that, but we only measured it in an area this big, so it may be just a local phenomenon. I think the carbonates that have been seen from orbit are, if I'm not mistaken, magnesium carbonates and not calcium carbonate. Is that right? Yeah, I think that's right. There's another question back here? Same question? Well, this is much more difficult for us. We didn't get enough water into Tiga to really see that very tiny deuterium signature and make a real measurement of it. So I suspect, and I'm very sad about this, I suspect we won't be able to get a D to H ratio, either there or in the atmosphere, as I understand it. Well, thank you. One more question. Now, that would be a nice number to know, wouldn't it? Well, we don't know from our own mission just how thick the ice is. We have some indication from the Odyssey experiment that it probably goes down as much as a meter, but below that we'd have to go with the radar experiments that are in orbit, and I'm not sure what they're able to tell us about the ice, but I think you'd have to ask them. Well, we know something about the strength of the material because our robotic arm was wired with torque measuring devices, measuring the current basically, and it's a very strong material. Ray tells me it's 5 times lunar soil or something. The cohesiveness, yes, 5 times lunar soil, so it's a very cemented layer on top, so I would suspect that the density of it is higher than it, much higher than it'd be for a very loose soil. But answer's coming in a couple of months, Bill. You've caught us kind of mid-analysis stage here. AGU wasn't quite placed just in the right position in the calendar for us. LPSC will be much better, and I hope to have more definite answers by then. Are we running out of time?
We've got a couple more minutes if you want to take one more.
Yeah, it's not so much the clouds, it's the interaction of the ices with the soil. Interacting with the soil, and the ice table really controlling climate locally. Yes, yes, and the disequilibrium snows that are occurring, and well, anyway, I really don't want to blow the whole story because the Canadian team is still developing it, and it's too early to really release it. I think in 2 months. Yes. Yeah, it's the potassium, chlorine, sodium. We're not sensitive to every one. We can't measure nitrates and phosphates, for instance, but you know, we see many of the others. We suspect there's some sulfur in the soil, although it's in a form that we're not very sensitive to it, and so we're not 100% sure there's no sulfur of any type. But we didn't see lots of sulfates at the 5 or 10% level as we suspected. But we have a lot of the nutrients that are usually associated with life.
Well, thank you again very much, Peter. Thank you very much. Thank you.